Okay, so today we're talking about ions. Last day we talked about atoms and atomic theory. We talked about how in the nucleus we have protons and neutrons, and in orbit around the nucleus we have the electrons, and that we can draw Bohr diagrams, and now even more conveniently we can draw Lewis diagrams that determines how many electrons there are in the outer orbit of the electron. All right? So now Lewis diagrams are our friend. Now I'm going to use Bohr diagrams to illustrate something here, but in the end I'm going to go right to Lewis diagrams, because Lewis diagrams are far more convenient and they really tell us what we need to know about an atom. It's the outer electrons that really is what takes place in chemistry. Chemistry happens when atoms gain, lose, or share their outer electrons. We don't care about the electrons that are on the inside. They're just their outer electrons. When copper 1 turns into copper 2, it's giving away one of its outer electrons. That's what turns it into copper 2. That's chemistry. That's a chemical change. So what we want to talk about today is what happens when atoms lose or gain electrons, and the answer is they become ions. Just a little quick review. How many outer electrons do the atoms in group 1 have? 1, because they're in group 1. 2 in group 2. We ignore the transition metals. 3 in group 13, but I'll often just call it group 3. We often say that groups 1 and 2 and 13 to 18 are the main group elements, in that we don't worry about the transition metals. In this course, we're not worrying about the transition metals. We might talk about a few of these in here, but we're not going to worry about their diagrams, etc., etc. So we're talking the main group elements. Boron, aluminum, 3 outer electrons are 3 dots, 4 dots, 5 dots, 6 dots, 7 dots, and 8 dots around these guys, except helium is the special case. All right. Let's advance here. Let's talk about how ions are formed, and you can write this all down. This is all good information. Noble gases are non-reactive because their outer orbit is full. Other elements are reactive. Did I say reactive up there? Noble gases are non-reactive. Other elements are reactive because their outer orbits are not full. Metals tend to gain electrons. Non-metals tend to gain electrons, and metals tend to lose electrons, so that their outer electrons is full, or their outer orbits are full. Man, I'm having trouble reading my own note. When it is full, it is stable. Did you talk about this last year at all? About gaining and losing electrons? All right. Does anybody remember? Were you taught a reason why? And I'm just kind of asking you here, like sometimes teachers go through discussions like beryllium, let's say beryllium, or even magnesium. How many outer electrons in magnesium? 2. So, the question might be, well, why would magnesium then tend to lose 2 electrons as opposed to gain, like how many would it have to gain? 6. Why would it lose 2 instead of gain 6? What do you think, Megan?
Because losing 2 is easier.
And that's what you would have been taught, right? Somebody would have said, well, losing 2 is much easier than gaining 6. And that's fine. But what I find when I teach my grade 11 is I have to train students out of thinking that way. Because ease of losing or gaining, again, implies that the atoms have little brains and that they're lazy slobs, right? Oh, man, I got to go around looking for 6 electrons. Jeez, that's going to take forever. Somebody want my 2. It's much easier. Somebody take my 2 electrons. And that's why I tend to try to use or try to avoid using this, easier, because it really doesn't have anything to do with ease. But you know what? Sometimes it doesn't hurt to think that way. Often we do that. We take an inanimate object and we give it some kind of human characteristics that helps us remember. So, just like, there's also another thing that young chemists are often taught. And what do we say about the atoms once they've lost their outer shell or they've filled it up? What do we say about them? Yep, they're happy. They're happy. Magnesium wants to lose its electrons because it's a lazy slob, and that once it gets rid of it, it's happy. Like those 2 outer electrons were just driving it crazy. Like, oh man, goodness. Now, keep in mind, atoms don't have little brains. They're not lazy slobs. They don't have any emotions. They're not necessarily happy or sad, right? But we do describe it that way to make it easier. You'll learn next year that the reason atoms lose electrons or gain electrons has everything to do with the laws of physics. It has everything to do with the amount of force that's holding those outer electrons to get onto the atom from the positive nucleus, right? So the nucleus is positive, and the electrons are negative, and they're being attracted to that nucleus. That's what holds them close to the atom. And some atoms have different sizes, and therefore those electrons are further away, and that makes the loss of an electron either easier or harder, all right? So it has everything to do with the laws of physics. Now, I'm not going to teach you those laws of physics right now. I'll teach you that in grade 11. But the reason that, something like magnesium, right, loses electrons has a lot to do with where its electrons are positioned and what other atom it's up against when it loses that electron, right? Because we also need to keep in mind that atoms lose electrons to other atoms in kind of a tug of war, all right? You put a magnesium up against another magnesium, nobody wins that. Everybody hangs on to their electrons. But you put magnesium up against a chlorine, and magnesium loses the tug of war every time, because magnesium's attraction to its outer electrons is significantly weaker than chlorine's atoms for its empty holes in its outer shell. So it wins the tug of war and gains magnesium's electrons. But you know what? That's for the future. But being that I know what you're going to take when I see you back here in grade 11, I'm just telling you the way it really is. All right? It's okay in this course to think about being much easier to lose 2 than gain 6, and it's also okay to think about being happy because we've got a full outer shell. That's good stuff. So I'm just telling you though, we don't have little emotion. Atoms don't have emotions. They don't have desires. Oh man, I wish I had that outer shell. They're jeepers. But that's not a bad way of thinking of it. All right, that's why I say things like they tend to gain electrons, not that they want to gain electrons or, that type of thing. All right, so let's talk a little bit about what an ion is. A charged atom, positive or negative, formed by changing the number of electrons in the outer orbit, gaining or losing. A scientist by the name of Michael Faraday, one of the most awesome scientists in all of history, was working with electricity and using electricity, kind of like that Huffman apparatus. You guys saw the Huffman apparatus last year, the electricity to separate the hydrogen from the oxygen. Faraday would have been using a device like that, and in order to kind of explain what he was seeing, he imagined that there were these little charged particles in the liquid, and he was correct. And he imagined as if they just kind of wandered around in the solution, and when the charge was started, that the positives went one way and the negatives went the other way. And the Greek or Latin term for wanderer is an ion, and that's why Faraday used the term ion. It means wanderer, and they tend to be in aqueous solutions or in water-based solutions, and they tend to float around and move around and wander. Okay, so positive ions. That's pronounced cation, and the cat part of cation comes from the name of one of the electrodes. One of the electrodes in a device like that is called a cathode. I don't know if you've heard of that term before. So cations tend to wander towards the cathode. That's the historical origin of the term. You don't have to worry about that. I see the big T in the middle of it, and I think it looks like a plus. That's how I remember it's for the positive ions. That's just me. I've heard of all kinds of explanations. Well, cats are nice. They're great. I love cats. That's positive. I'm like, what? Are you kidding me? Like, I hate those cat pictures on the internet. Like, cats, more cats. I'm with the positive part. Yeah, my Kleenex box has cats on it, doesn't it? What the heck's with that? Not by choice. Here, fix that with my Sharpie. What can I do to this cat? Give it a mustache. Anyway, cations have positive charge. They're formed by removing electrons. Metal atoms tend to lose their electrons and form positive ions. The next slide is a little picture of an example of using Bohr diagrams. Now, we're not going to do this all day long because Bohr diagrams are too long, but this is something that I think is sometimes overkill, and you might not need to write it all down. Let me just show you what I'm talking about. So just put EG. Again, every time I put example, just put EG. And sodium, you can even put Na there if you'd like. If you want to shorten your notes up, by all means do that. So if I take a look at sodium, we're looking at element number 11, and this is supposed to then be plus 11 to represent the charge in the Bohr diagram. Don't write what's down in the bottom of the box here, all right? And just a reminder, how many electrons in the first orbit for sodium? 2. And how many in the second? 8, because it's full. And how many in the third? 1, and we put a 1 right there. And as sodium bumps up against maybe a chlorine, we're not talking about what the other element is right now because it's got to be a tug of war. Sodium does not just lose its electron out to nothing or nowhere. No atom can just lose its electron to nowhere. It's always got to lose it to something. So let's say it's losing it to something like chlorine. So it's lost the tug of war, plus 11 to 8. And you'll notice now that I have one more positive charge than I do negative charge, and that makes the charge plus 1. So I'm going to just write underneath here, right, we have 1 more plus or positive than negative, therefore plus 1 charge. I think that's enough information other than what we've got in these boxes. Sometimes we have too much information. Na needs to lose 1 electron. That's obvious. Na now has 11 protons and 10 electrons, giving it a plus 1 charge. 1 more positive than negative, plus 1 charge. Okay? If it gives away 1 negative from neutral, it becomes plus 1. Okay? We're okay with that? I've taught this at many levels. Sometimes students struggle with that. How can something become plus when it gives something away, right? Because sometimes they think when something is given away, you should have less. But when you give something away that's negative, you actually get a positive charge, right? See what I'm talking about? So, what's that? It is. It's integers. It's exactly like that. But perhaps we have students that aren't good at integers. So I like to think of it as if like the atoms are hippies, right? So like let's say sodium, is a hippie atom, and says, "Hey man, I'm just feeling terrible, man. Just feeling down." And maybe his buddy says, "Hey man, if you're feeling down, just push that negative away, man. Just push that negative away. Just push it away, and you'll feel better, man. You'll feel better." "Okay, let me try that, man. That sounds cool." So he pushes one negative away. "Hey, you're right, man. I feel better. I feel positive." "Yeah, thanks, man." "No, you're not buying this?" "All right, I'm sorry. I just thought I could help." Those of us who aren't good with integers. All right. No hippie atoms. Oh, I do want the name underneath there, and I apologize. The name of this ion is then called a sodium ion. All right, just put it in there somewhere. So the name of the ion formed is called a sodium ion. So a sodium atom loses electrons and becomes a sodium ion. Are we okay with that? All right, so Lewis symbols. Now we're going to get to the easy drawing here. We don't need all those inner electrons. Now don't write right away because I want to see what I want to do here. Ah, yes, excellent, good, good. This is good. I had a nice little chart for you to fill in. Again, if you went online and printed the chart, you're in good shape. You're going to the chart. If you didn't go online and print the chart, then you're going to have to create lots of little boxes on your paper in order to fill it in. Which is, I know the way Jaden works. All right. So you don't need to write positive ions on the periodic table. This was a sheet that was online. If you don't have the sheet, you're making kind of a table. You don't need all the boxes in there. You could write it along horizontally. We're going to start with group number 1. All right? What's going on here? That's what you want. Group number 1. So, again, hydrogen. Lewis symbol, H. How many dots? 1. How many electrons is it going to lose? Number of lost electrons. Yep, 1. Lewis symbol of the ion. Whenever you draw a Lewis symbol of a charged object, you put square brackets around it, and you put the charge outside. You can put +1 if you'd like, but you don't have to. Plus is good enough. Name of the ion. Positively charged ions keep the same name as the atom. The negative ones get an "ide" ending, like chloride. But positive ones keep their name. This is then a hydrogen ion. It's that simple. Lithium. How many electrons is it going to lose? 1. We're seeing a trend here. Anybody see a trend? Anyone? Anyone? Go ahead and complete all of the group 1 ions. We're not going to go into rubidium and cesium, but we could, right? But we don't need to go, it's a trend. Same name. Roll on group 1. I'm not going to do all of it. I'm going to just do the ions here. And A. Notice in the Lewis diagram of the ions, I put no dots because they've lost that dot. There's no dots there. And K, yeah, that's supposed to be square bracket. But that's the ion. Any questions or concerns? Group 2. Actually, this contains group 2 and group 3. I think. How far down do I go in group 3? Yep, no, that's group 2 and group 3. Beryllium. How many dots? 2. It's not like helium. They don't go beside each other. They're not paired up yet. They can go opposite sides if you want. It's not a big deal. Or you can put it at 3 and 6. It doesn't matter. You can even put it at, like, if you wanted to be crazy, you could put it like at 6 and 9. It doesn't matter as long as they're in 2 different positions. How many electrons is it going to lose? 2. Be, no dots. What's the charge on this? How positive is this guy going to feel, man? 2 plus 2 plus 2 plus 2. Name of the ion, no change in the name. It's still positive. It's a beryllium ion. You could do the rest, and you're going to in a minute, but let's just jump down to this one for a minute, so that then you can finish it off. How many dots around boron? How many dots? 3, right? 3. I know I'm not doing the hands up thing, right? I could, okay, Sammy, how many dots around boron? But the way I see the look on your faces, I'm thinking this is rolling along pretty straightforward. So I don't feel the need. I need to, wake anybody up. How many electrons is it going to lose? 3. B. Charge plus 3. And a boron ion. Boron ion. Go ahead and complete the rest. Again, I'm just going to put the Lewis symbol and the ion name in a moment. And there are some questions at the bottom just to get us to think about the charges that are involved. So if you can answer those, by all means, go ahead and give it a shot. We'll answer that in a moment. I screwed that up completely. Ooh, that's exciting. The eraser hasn't worked in a long time. Telling me it's going to work? No. Any questions or concerns? Again, I'm hoping that we can see a trend. Group 1, when it becomes an ion, it had 1 electron in the outer shell, becomes a charge of +1. Group 2, which had 2 electrons, becomes +2. And group 3, which had 3 electrons, becomes +3. Okay? And is that the questions that are on the sheet? So what type of elements have we been dealing with here? Yep. Sorry? Non-metals? Which side of the world is non-metals? It's on that side. Try again. Metals. Metals is correct. Metals. Metals create positive ions. Group 1 +1, group 2 +2, group 13, or group 3 +3. Okay? And there's that grouping right there. I think I already sent it up. You can write that stuff down there. 1 second. So we'll talk about negative ions. What do we got? As they're writing, we'll give them 1. Let's see.
You know, 118. No class?
118. They don't have a class right now.
No.
No.
Okay.
Why was everyone worried about the small bucket? It was a little pale. Very good. Very good. Nice stuff.
Right here.
Is it cool enough?
Yeah.
Sunny or rain?
Sunny.
Sunny? All right, we'll take it. Okay, now to the other side of the world. We're talking about the nonmetals. Anions. Anions are negative. How do I keep that in mind? The letter N jumps out at me after the A, and that makes me think of negative. Anti, like the opposite. Yep. Where it actually comes from, I told you cations came from the one electrode being called a cathode. Electrically speaking, when they first were creating, these batteries, the other electrode is called an anode, right? So the terminals of a battery are actually called anodes and cathodes, and those words came first. And then as Faraday was working with these solutions and imagining what was taking place, he imagined that the cations went towards the cathode and the anions went towards the anode. So that's why they're called anions. That's where it comes from. But that's another way of thinking of it. Anti. Yep. Yep. The words cation, the cathode and anode, if you wanted to maybe think about where that came from, it has to do with the way they imagined the electricity moving up one of the charged rods of the battery and down the other, because it has to go up one and down the other. And ana means to move up by so if you've heard of like anniversary, they have an anniversary, it means the year is moved up by 1. So the anode had the charges moving up and the cathode had charges moving down. That's the origin of the terms, but you don't have to worry about that stuff. They do come from somewhere. But anyway, that's the way I think of it. I think of the N. All right, they have negative charges. We're adding electrons until they're full. Nonmetals tend to gain to form negative electrons. Again, I've got a little example here with a Bohr diagram so that we can see it, right? And then we're just going to go to the Lewis. Again, I don't think there's necessarily a need to write this down. Fluorine is +9, 2 and what? 7? 2 and 7. And it's going to gain an electron so it can be happy. Well, anyway, you get the idea. It has a strong pull on neighboring electrons, is what it is. We call it electron affinity. It has a great affinity for neighboring atoms' electrons. So +9 to 8. And now, essentially, the way I like to put it, we've got like 1 more, right, negative charge than positive charges. 1 more negative than positive charges. Therefore, -1 is the charge. Again, I'm going to advance the slide here. A box is going to come up explaining that particular thing. I think that's overkill. Yep. Valence shell. Excellent. Valence means outer shell. All right? And that's not a bad word to write down. Valence shell means outer shell. Okay? It's the outermost shell. Again, I like to know where words come from. They help me remember things. Valence shell, the valence years ago, before even the knowledge of electrons, was linked to how well it could bond to other atoms, how many atoms it could bond to. Carbon could bond to 4, and nitrogen could bond to, carbon could bond to 4 hydrogens, nitrogen could bond to 3 hydrogens, oxygen could bond to 2 hydrogens. They knew that. And the term valence meant the power to bond with, all right? Its ability to bond with stuff. I think valence comes from the same root word as valor, right? And Valhalla, which is where dead, Vikings go or something like that? Isn't that where dead Vikings go? Anyway, it represents a place of power, right? And so valence means the power to bond with. And once electrons were discovered, chemists realized, oh, this power to bond comes from the outer electron. That's what gives it its power to bond. So the term valence was then transferred to mean the outer shell, because that's where it gets its power to bond, from the outer electrons. So valence means outer shell. Okay? All right. In terms of the name, it's a fluoride ion. So negative ions get a little bit of a name change. They get an "ide" ending. And I don't know where that comes from historically. I should know that. Why don't I know that? I don't know. Got to track that down. I don't know where the "ide" part came from. Did they even know it in Lavoisier's day? Maybe. I'd have to read deeper into the book to see if he named chemical compounds that way. No sweat. We're not worried about that right now. If it's negative, we put an "ide" on the end. Is it that stimulating? We're clock watching, are we? Megan's clock watching. Excellent. 1:58. Oh my God. That's 22 minutes. What's that? Yeah, that's it. That's all it is. 1:58. It's dragging. 201 on the outside world, not in the school world. We've got still 2 more minutes to catch up with the outside world. Write that down. Don't be distracted. These are negative ions. They're awesome. No, you don't. If you've got it printed off, then you're going right to the page. Question? Nope, just stretching. All right, no problem. Don't be you're all terrified that I'm going to point you out, and you should be. That's the fun part of my job. Watching you guys squirm once in a while. That's fun. It's fun. No? All right. So, starting with carbon. Now, carbon and silicon are in group 4. And we're going to have them gain some electrons, because we're talking about negative ions. How many dots around carbon? 4. 1, 2, 3, 4. And how many electrons does it need to be happy? 4. It's going to gain 4 electrons. Now, the Lewis symbol is now a little different, because it didn't get rid of its 4 dots, it's gained 4 dots, which means now I'm going to put a full 8 dots around that carbon as if it's a noble gas, because it has gained those electrons. I do complete it with square brackets around it, just like the other one. And now that it's gained 4 electrons, what's that? Yeah, the dots go on the inside of the square brackets. It's like it's like the square brackets are not part of the Lewis diagram, but what the square brackets are doing is it's saying this whole thing that we've encapsulated inside, this picture, is the ion that we're talking about. And what it's encapsulating is the charge. What's the charge if we've gained 4 electrons? Yep. Negative how many? Oh, no, we've only gained, how many electrons did we gain? Negative 4. It started with 4, now it's got 8, it's only gained 4, negative 4. You're not just counting the dots, right? You're counting how much it's gained. Negative 4. Yeah, very good. It's a carbide ion. Let's do silicon before I jump down to the nitrogen one. Si, 1, 2, 3, 4. I don't think we're too surprised in that it's going to look very similar. This is a tongue twister a little bit. Yeah, what do you think, Kenzie? Silicide. Yeah, very nice. Silicide. silicide ion. Now, notice at this point, if we move down, we're going to hit germanium and tin and lead. And germanium and tin and lead are metals. They will actually tend to lose their 4 outer electrons. And what charge do you think those guys would become? What do you think? Positive what? Positive 4. Positive ions, I like that. That's a good answer. Positive 4 plus 4 ions, okay? All right? Even though when they lose their 4, you might think they end up in here some way, how they lose them, but it's simpler than that. It doesn't have to be that complicated. These guys down here actually become plus 4 ions. Carbon can do the plus 4 maneuver as well, but you've got to put it with you've got to put it with an atom that carbon's going to lose the tug of war against, right? So it all depends on what atoms you put it with. You put carbon up against hydrogen, and it wins the tug of war, and it takes hydrogen's electrons. But you put carbon up against fluorine, and it loses the tug of war, and carbon becomes the plus 4 ion. So these middle guys can be plus or minus 4. In this case, we're writing them down as minus 4, okay? How many dots do you think for nitrogen? 5? 1, 2, 3, 4, 5. How many do we need to gain to be happy? 3. Now again, full. And what charge does it become? Yep, Mackenzie?
Nitride ion?
Yeah, that's the name. But what charge does it become after?
Negative 3?
Yeah, negative 3. Gain 3 electrons, negative 3. Nitride ion. Go ahead with phosphorus. Notice the difference though. For positive ones, to tell what the charge is, it's really easy. All we have to do is look at the group number. For the negative ones, we have to think, how much does it gain to get to full? So we see group 15, it's going to gain 3, negative 3 for that run. Okay? Oops, screw up. Can't erase. Name of this one. Phosphide. Phosphide. That's all right. Phosphide ion. Jaden thinks it's a one-on-one teaching situation. That's why she fires out all these answers here. She thinks she's the only person in the room. But if you take a look behind you, you've got some friends back there. You can see them. Yep. It's tricky. It's tricky. I'm going to tell you the name and you're going to learn it. Yeah.
Okay.
Yeah. It's not phosphoride. You might think it could be phosphoride because we just got rid of one syllable on the end of the others, right? You see what I mean? But it's not. It's phosphide. So you're learning it. All right? Do you need my guidance? Or can you follow the trend? What do you think? How about someone other than Jaden? Tell me what I'm going to put across this whole thing. Anybody brave enough to try that? Oh! Except for the last one, for the name? That's okay. You give me what you got, and I'm going to get a name here on this one. Because Emily. What do you got, Emily? Tell me what to draw here. Yep. Yep. And I'm going to assume that you know where to put them. Okay? Yep. Yeah, nice. Very nice. This is an easy one. This is an easy one. Oxide ion. Oxide. I would think it was an easy one. I want to jump down to F. so that then you can then complete it. Somebody have F all the way across? Yep, Mackenzie, what do you got?
There would be 7.
Yep. Yep.
There would be 1.
Yep.
There would be 8 software and this bracket. Again, that's not that correct. -1.
Yep.
And fluoride ion.
Yep. Fluoride ion. I have to say it like that or I spell it wrong. Normal human beings would just say fluoride ion, but I have to say fluoride because in fluorine, I have to say it that way too in my head, there's a U before the O, and if I just say fluorine, I forget about the U. It's the spelling thing. It's like muscles. I got to say it that way, and skizzers, right? And sugar. You know what word I'm talking about for sugar? Sugar. Sugar. Got to say sugar for sugar. What's that? Bologna. Bologna. Correct. Yes. All right. Go ahead and finish that off. Yep. Yeah, very good. Sulfide. Sulfur can also be spelt with a PH. It's both ways. Yep. You don't show anything. That's right. You would draw it, and you'd actually put electrons gained, 0, and Lewis symbol. I would just put a line through Na, not applicable. There is no iron or ion. Name of ion, don't even bother with it. Yep, put a line through it. But you could draw the Lewis diagram for the noble gas. Do I need to fill in the rest of the squares? Really? Do I need to? For well, I'm on the next slide. I mean this one here. Do I need to put any in here? What's this called? Chloride ion. Chloride ion. No need for the U in that. See, it's just a chloride ion, not a chloride ion. Okay, what do we do with these? Right? Helium, 2 dots together, special case. Electrons gained, none. Don't even bother with it. Doesn't form ions. Okay? And that's going to be true for the rest of them as well. Neon, 1, 2, 3, 4, 5, 6, 7, 8, none gained, nothing. Sorry? On yours? Excellent. Maybe we shortened it up. Now, hydrogen's a special case. Hydrogen can lose 1 and become a hydrogen ion. We already saw that. But hydrogen actually can exist also in this position on the periodic table, right here. It has the chemical ability to gain an electron as well. So let's go through the procedure as if hydrogen was a gainer in this case. So hydrogen, right, we've seen that, and it has the ability to gain 1. And when it gains 1, it's going to look like helium. They're paired up because they can only put 2 in the first orbit. Square brackets. What's the charge around this one? Yeah, Mackenzie? -1. It gained 1 electron and therefore -1. -1. And what's the name of this guy going to be? Again, Jaden's in the class on her own. She's correct. It's a hydride ion. Hydride ion. I might have to create a Hermione Granger award, and Jaden would be the winner of it. Okay, that's right. That's fine. So we can have hydrogen ions and we can have hydride ions, depending on whether it gained or whether it lost. Okay? All right. And what type of elements form negative ions? Non-metals. Non-metals. And now for the charge. Now let's do the whole charge. The whole charge chart. Elements in group 1 tend to have what charge? We're going all the way across, right from the beginning. Elements in group 1 tend to have +1. Yeah, we'll do hands up. Put hands up. I got to learn names here. Hands up. Group 2. Yeah, Olivia. +2, because I just about burnt Olivia. And I know Megan. Sammy. Positive 3. We're going out on a limb here. People I don't know. Nope, no good. Oh. Sad, isn't it? It's quite sad. Kendall! Oh, Kendall, what do you got? Sorry? It can be +4. That's correct. If it's one of these guys down here, what else? Yep. -4. I didn't go for a new person on that one. We'll go for a new person now on the next one. 15, what's the charge going to be? Connor? -3. 16? Allison? -2. 17? Emily? -1. 18? I'm going to pick on Alana? 0. No charge. Nice. Okay. Don't mind that. That's the periodic table that different teachers have used in the past. But if you go on to our site, actually write down the homework, and I'm going to show you the periodic table that I have chosen for this class, and it's different than this one. And some teachers in the past have supplied you guys with periodic tables that have the nice charges on the top. I'm not doing that. I'm not giving you those charges. You can either figure it out, or I'll show you where you can find the charges on the table. All those charges that we talked about are on every periodic table. You just need to know where to find it, right? And the charges that are given, these charges that we've calculated, are sometimes called the valence, same as the valence shell, it has to do with the charge, the power to bond, and another term that they use is the oxidation state. Now that's the term that's more common in higher level chemistry. The oxidation state historically comes from how the element reacted with oxygen, how much oxygen it grabbed up when it was combusted, okay? And we now know that the oxidation state, the charge, is related to how much oxygen it can grab up. So that's why we use the term oxidation state. And I'm going to just bring up on the PowerPoint here. Let me just flip here. Let me just bring up here. So if I go to, I'm still talking here, still doing exciting stuff. If I go to our resource materials, and I now go to our periodic table, if it comes up, internet is crawling. So here we've got junior periodic table, and it would be a good thing to print one of these, folks. Let me just bring it up here. And this doesn't work very great, so let me just download this, because I'm just going to download it in a PDF viewer. Be patient with me here. And did it open it up? Come on, open it up. Okay, so if I now zoom in, all right, take a look here. Take a look at hydrogen, all right? Right here, it says possible oxidation states. That is the charge. Notice for hydrogen, it says ±1. That's what we just talked about. Notice for all of them in group 1. All of them in group 1. And now we can also see group 2. +1, +1, +1. +2, +2, +2. All right? So they're all on the table. They're all there. As I shift over to the other side here, boron +3, +3, gallium +3. Now notice carbon. A lot of the nonmetals have many different oxidation states. It means that depending on what type of chemical compound they're in, they can actually share more complicated ways than I've taught you. In this course, though, we're only going to use the simple ones. But look at carbon. Carbon can be ±4, like we talked about, but it can be +2 under special conditions. And you don't have to worry about that now, but you'll learn about that in the future. Same look at with silicon, all these different ones. Look at nitrogen. Nitrogen can be +2, +3, +4, +5, -2, -3. It's crazy. Nitrogen can be all kinds of different ones. You will learn how that works in the future. But for now, in this course, Nitrogen is in group 15, it's -3. Phosphorus is -3, arsenic is -3, okay? So for your course here, just the simple one that I've taught you. But in reality, some of these chemicals can bond in more complicated ways. Oxygen, -2, that's all it can do. Sulfur, it's more complicated. It can bond all kinds of different ways. But notice it also has -2. They're always at the end, -2, -2, -1, -1, -1, okay? And look at 0, 0, 0, right, along for those guys. So you can find all of those charges on the table. Just looking ahead to the near future, we're going to talk about things like copper and nickel and cobalt. And like I said earlier on in our experiment, there's a copper 1 and a copper 2, and that's what we used in our experiment. It was a mixture of those two, copper 1 and copper 2, and then it all turned into copper 2. Okay, excellent. Those are ions, and that's a good place to end. Did we get the homework written down? All right. So tomorrow now we're going to put the ions together. Right now we talked about the ions on their own. Tomorrow we will put them together and we'll make compounds. We'll talk about how compounds are formed and how we can write them out in their names. All right? Perfect place to end.